Good afternoon, everybody. What I'd like to present today is a two-dimensional coupled model for submarine debris flow and its interaction with the subsea installations. It's a topic mainly deal with the deepwater environment, but I know that most of the coastal communities are primarily interested in shallow water environment, but this particular topic deals mainly with the deepwater setting. But I hope this will be interesting to you. So what are some of the issues? Here I'm showing you a cartoon pictures of an oil and gas platforms. Here you're looking into the manifolds. Over here the risers, the platforms, all other different equipments are sitting in a nice smooth seabed. But in reality, seabed is not like that smooth. It's very unlikely. Typically, the seafloor is very unstable like this. Here you are looking into a continental Gulf of Mexico continental slope. If you like to orient yourself, the Galveston is right around here, and we are talking about hundreds of miles offshore to the continental slope, where you can see the rugged slope and the very unstable slopes over here, which has potential for movements and impact into a subsea facility. So textbook definitions of some of the failure mode. So here you're looking into this continental slope where the seafloor can be unstable and can trigger some sort of failures, and this failure can move as a slide through the favorable slope, or it can form a slurry or slump and then move further downstreams if the slope is favorable. So sometimes those slump can form a thick density debris flow, or it could be even sometimes it can form with the ambient water, and the density could be low, and this form also the turbidity current. So those are typically the debris flow and the turbidity current combined together. They call it a mass gravity flow. So these are kind of gravity flow that moves downslope through the as a gravity flow. Again, so issues with this type of flow, which you call it mass gravity flow, is their potentials to impact the subsea installations. What you're looking into the oil and gas, all those crisscross lines are basically the oil and gas facilities into the Gulf of Mexico. There are lots, and they're also sitting into a very unstable sea floor, which moves and has potential to impact the facilities. So the main issues, if I would like to make a statement over here, so most of the cases, ocean bottoms are associated with highly irregular and unstable surfaces with steep slopes, and unstable sea floor and other natural activities result into underwater currents. We call it mass gravity flow, and affect subsea facilities. So there are a lot of questions to address, how to simulate those movement of debris flow, and how to evaluate the impact force, and how to characterize the pipeline responses. So to address some of these questions, what we did, we developed a coupled numerical model, which I'm going to present today. So there are a lot of challenges into this type of modeling because these are primarily the episodic events, and it's very difficult to get in situ measurements. Typically oil and gas industries may have some data, but it's very difficult to obtain. Extensive field work, geophysical code, and subbottom profile, which is expensive, is needed to understand the past deposits. Typically what we do, we assume that the deposit volume is also a failure volume. So this is one of the primary assumptions that we do for calibration of this type of flow. So this model is formulated based on the thin layer approximation of the Navier-Stokes equations. So there are mainly two layers. One is the plug layer, the other one is the shear layer. In the plug layer, the velocity is assumed constant. In the shear layer, the velocity is assumed to be parabolic, and those flow moves on a non-erodible layer. So this is one of the primary assumptions that we have. So that means the flow doesn't have any signature from anything that is coming from the bottom. So here are the equations we are solving in 2 dimension. Here is your source term, which is the trigger volume, that is the failure mass. You have this advection terms over here. You have this densimetric pressure terms around here, and it's counteracted by the bottom stress, and also here is your viscous terms. And the challenge is the bottom stress, which depend on the flow structures and the rheology of the flow. And for this, some theoretical work was needed to close that. So for the rheology, we use the Herschel-Berkeley model, where it defines that the bottom stress is a function of the flow structures in the vertical directions. Had introduced a non-dimensional parameter called the zeta, which is basically the defines the thickness of the shear layer and plug layer. With some analytical work, we come up with the velocity in the shear and the plug layer as a function of the thickness z, and this is the closed form, this one which we solved numerically. So for the flow structure introductions, we also have to solve for the impact force, and for this one we calculate the fluid drag and as a function of the Reynolds number. But again, there's some lot of parameters over here, A, B, C, which needs to be resolved. And for this one, we also had to do some CFD work to close the A and B and C, the empirical parameters. So we did some exercise with ANSYS Fluent to understand the fluid drag coefficients as a function of the Reynolds number. So here are some results against some limited experimental data that were obtained. So this shows an empirical relationship between the drag coefficients and non-Newtonian Reynolds number, which has been used into the current model. So this is the modeling framework. The first one is the flow component or the module, and the second one is the structural component or the structural introductions, and they are coupled to analyze the pipeline movement subject to debris flow movements. So for the model validations, we relied on the laboratory experiments by Morik. So it is a plume experiments on an inclined slope. We looked into the deposit thickness over here, the runout distance, and also the frontal velocities on the experimental data. In general, the numerical exercise represents the experimental results fairly well. We also tested our numerical model against field data collected by Pirmes in Nakika Basin. Here we tested the runout distance and also the thickness with the scale of the problems, where the deposit thickness are hundreds of kilometers from the slope. We are kind of happy to see that the model represents the data reasonably well. Next, we applied our model into some prismatic test bed. So here you're looking into a test bed, fairly uniform slope, and with a placement of a trigger volume and how debris flow moves down slope. And since this is a 2D model, you can see the distributions of the debris flow both along the x-axis or the downslope, and also both in the lateral directions. With the help of this model, then we are able to understand the influence of different parameters into the runout distance. So in your left pictures, what you're looking into, as the viscosity or the yield stress increases, the runout distance also decreases. However, as the initial height increases or the failure mass increases, the runout distance also increases, which makes sense because you are putting more gravity force into the dynamic flow dynamics, which makes the runout distance high. The next exercise we did is on a couple of different configurations of a canyons. So here you're looking into a narrow canyons compared to the wide canyon over here, and distinguishing flow characteristic as you see on your right side. For example, in the narrow canyon flow, we see a lot of spillages from the canyons over here, but as per the wide canyon, most of the flow is remained within the canyon, and very little spillage that we have observed outside the canyon. So this kind of information is important to understand some of the avoidance zone as you plan for a pipeline routing. We can also extract crucial parameters along a pipelines such as strain or displacements. Here we put some pipelines along the model testbed with the red lines showing around here. This is the uniform slopes around here. The pipeline is routed parallel to the slope, and the other one is along the canyon, and these are the failure mass. So this shows some of the results from the testbed exercise that we did. Pretty busy slides. It also shows on your left panel, it shows the pipeline movements and the position of pipe under different pipe materials. And on your right side, it shows the displacements. As you see that PVC pipe has the more displacement compared to the reinforced pipe. And also on your bottom panels, what I'm showing is the displacements as a function of the pipeline length or the positions. As you see that along this particular locations over here, the displacements of the pipe is more or the highest compared to the other locations over here, because the debris flow has not impacted these segments over here. So these are some of the information is very crucial to understand some of the avoidance zone that that goes into the planning of pipeline routing. So what I presented here is a two-dimensional coupled mass gravity flow model that is very useful to understanding the quantitative geohazards, basically to map the areas into the continental slope that has potential for failure, and also some of the avoidance zone that could be going to the planning of routing of the pipelines or subsea installations. I'd like to acknowledge my former student, Dr. Kiwan, for most of this work, and also this research was supported by many companies like Fugro, Chevrons, and also Department of Homeland Security through grants to Jackson State University when I was employed over there. With this one, I close my presentations and invite any questions if you have.